Different day, you can tell. Different shirt. Yeah. You see, the last video, hopefully you're watching these in order, we were working on problem number 7 with the iodine. Okay? And we got down to the point where my battery ran out. I got a warning a little bit before that, but I didn't think it was like 1 minute and your battery dies. I thought I had 10 minutes left. Apparently not. The camera disagreed. Right? Bottom line is, I didn't quite finish that problem up. So now I got to finish that problem up. Now, I'm not going to go back and redo that whole video because it was pretty sweet up to that point. So let's finish up and do the math. We were just about right here. We had just determined that x is small and insignificant rule of 100. Remember? Gone. Then we had cross-multiplied these two, and we came out with 7.524. 7.524 times 10 to the negative 7th. There we're there. I know we had this, but I'm just reviewing. So that times that gives me that, and that's equal to square both, 4x squared. Solve for x. All right, divide by 4. So this goes away, take square root. And that's just about where the video went. Okay, so when we solve for x, you hit the thing out. Turned my calculator back on and it was ready to go, exactly where we left off yesterday. Well, I left off when I turned back around and you weren't there anymore. Okay, we end up getting that bad Larry right there. Okay, 4.34 times 10 to the negative 4. 4.34 times 10 to the negative 4th. Now you'll notice that if we look at the answers for this problem, that ain't one of them. Because that's not an answer. We have to take that x and put it back in to the equilibrium concentrations. This is the concentration at equilibrium of molecular iodine. This is the concentration at equilibrium of the iodine ion. You with me? You're all kind of twisted way over there. What you doing over there? There we go. That's better. All right, so let's put u in here. Well, just multiply this by 2. This by 2. If I multiply that by 2, I would get 8.68 times 10 to the negative 4th. So that would be one answer. That's how much of the iodine ion I would have floating around. And if I take the original equilibrium 0.0198 minus this, so minus 0.000434, we don't get much of a change. That'd be a 0.106, 0.96, 7319, 0.19. Okay, so that would be the other answer, or, well, 0.0194. Let's do that, 0.0194. Okay, there's our other answer. That's how much of the molecular iodine I would have. If we look at the answers, the answers here are just slightly different, like 0.72 as opposed to 0.68, and 0.0194 as opposed to 0.0196. And that is because when I did these answers out, I had originally did the answers out, to put them down, I used 0.02 instead of 0.0198. I used 0.02. And I made a slight difference. It's not going to make it enough difference for us to be worried about it. If we were an analytical chemist, okay, we'd have to be a little bit more specific. But what we need to do in our class, close enough for government work, we're good. If you can do that, I know you can get the answers, and you/me have done our job. Okay, so that would be the answers to that problem. And finishing up that problem, and I have full battery today, okay? I mean, me has a full battery and my camera. Oh, we're ready to go. Woo! All right, the last problem up here on the board in the black marker. Le Chatelier. Le Chatelier. It sounds very German. Okay, Le Chatelier, his principle, says this. Now, let me give you the Professor Gunner terms of what it says. If you scotch, I like that word scotch. If you scotch with one part of a reaction, the other part of a reaction freaks out because you're scotching with it and says, we gotta fix things because you scotched. That's Le Chatelier's principle. All right, makes sense, right? Okay, good. Let's take a look at the last problem for today. The Chatelier's principle. All right, now, I'll give you a more chemistry definition in just a minute. Relax, calm down. Okay, although I thought my definition was pretty good. You squish one side, the other side freaks out and goes, stop squishing. Okay, what do we got? We've got some phosphorus, pentachloride gas, plus, this is different. What's this? 92.5 kilojoules per mole. What? That's energy, people. That's energy. And I hope you realize kilojoules, it's heat. It's heat energy. Okay, heat energy. We'll talk about that in just a second. Reacts to form some phosphorus, trichloride gas, and some molecular chlorine gas. How are we doing for staying in the picture there? All right. Okay, there we go. Okay, so this is an equilibrium. That means everybody's happy. We got ourselves a happy little equation. Okay? Just as much reactants making product as products making reactant. Everything's just working like clockwork. Smooth like clockwork. Okay, smooth. Okay, I told you I used to be a stunt double for John Travolta in Saturday Night Fever. I'll stop. I promise. No, don't shut off. Okay, good. I won't do it again. Where was I? Okay, nice and equilibrium. So Chatellier's principle says, if you stress, I won't say scotch, but that's what it means. If you stress, that means change something in the equilibrium reaction, the reaction is no longer going to be in equilibrium. It will have to adjust itself so it gets back into equilibrium. So if you stress one side of a reaction, the other side freaks out and tries to adjust the reaction and get itself back in equilibrium. All right, I don't know what you're talking about still. All right, let's do an example. Okay, it says predict the direction of shift in equilibrium. Direction of shift, what are you talking about? Well, let's just say that we have these products here and we, do something to make them go away. Maybe we're trying to produce chlorine gas. And if we're trying to produce chlorine gas and we're producing, what would you do? Well, you would pull it out of the system, right? You would pull it, that's what you want. So you'd take this and go, yes, I got my chlorine, yeah. Actually, chlorine is a very poisonous gas, so be very careful. If you do that, then you're pulling out product. The reactants go, what are you doing? We just made you. Well, you don't do that. We're making you and you're leaving. So these have got to make more of that. That would be called shifting to the right. So when I say shift to the right, that means make more product. This is from your point of view. My right's over here, but you looking at me, the right is here. Shift to the right, make more product. Shift to the left, make more reactant. Okay, so that's what that means. So you hear me say that for all these problems. Shift to the right, shift to the left. Make more product, right, more reactant left. Okay. So let's take a look and see what happens when we switch with this nice, all happy at the moment equation. I'm going to skip A and go to B because A deals with temperature and I'll come back to it. We haven't done anything with temperature yet. Oh, by the way, if heat is on the left, it's a reactant. That's an endothermic reaction. Heat's going into entering the system. If you see heat on the right, it's a product. It's being produced. It's leaving exothermic, exiting the system. Okay, so let's just do B first, and we'll come back to A. More chlorine gas is added to the reaction mixture. So we're adding chlorine gas to the reaction. So, all right, so if we add chlorine gas, what does that do? Okay, so we're adding this. We're putting in more of this. What I like to do is, so we're adding more, we're taking our little, well, here's my chlorine gas in my jar. Let's take that and dump some in. Yeah. Well, we just added more chlorine, right? So what happens? Think seesaw. Okay, you remember, come on, when you were a kid, you might not have called it a seesaw, you might call it a teeter-totter or whatever, but everybody's been on a seesaw. We've seen them. If you haven't been on one, go on one. Take a break and go on and find one right now. Just drive around until you find one and get on it. Okay, you need to experience life. Okay, that was my pivot for my seesaw. Teeter-totter. So what did we just do? We just added more chlorine. It's like adding another, let's say you and your buddy and two others on the playground have a nice little equilibrium system. You know, you've done that in the playground, try to balance. Oh, look at what we're doing. Look how cool we are. All the cool kids do this. But then somebody comes in, they jump onto the seesaw. On this side, what happens? It goes down, right? So what we need to do is get this back into balance. So how are we going to get this back into balance? We're going to have to make more of this stuff. Make this side heavier and make this side lighter at the same time. We can ease up on this side and make more of this, shift stuff to the left, we will get it back into balance. So by adding more chlorine to the side, we unbalanced the reaction. Then we have to cause more of, we have to get this to start reacting faster because we need to chew this up. We need to use up this extra stuff that we poured in. So to use this up, we've got to make more of this. And that lessens this, which means this side goes up and this side gets made more of, so it goes down. Boom. Shift to the left. The reaction will have to shift to the left and make more reactant. Okay? Now let's go back to A. We can do A now. The temperature is raised or increased. So we're dumping in more temperature. It's like you take your jar of temperature and you pour more in because heat and temperature are closely related. And we'll talk about that in a little while, a few weeks from now. So we're dumping in more of this, like taking your temperature jar and going, here, have more temperature. So what does that do? Puts more of these two over here. We got more of this. This side goes, hey, we had a good thing going on. What are you doing? So these two have got to go, oh, relax, we got this. Make more of this to lessen the amount that we've added and make more of these over here to put it back into balance. So if we add product, or we add reactant, we're going to have to make more product to get rid of the extra reactant we added. That would be a shift to the right. All right, make more product to deal with the extra reactant that you added. All right. What do we got next? Bring it on, bring it on. Some phosphorus trichloride is removed. So maybe you're doing this reaction and you're trying to produce phosphorus trichloride. Earlier I used chlorine, but this time it's this one. And we're going to pull this out. We're going to say, take it. You're making this, yes, thank you very much. Pull it out, bottle that. Sell that for $80 billion a bottle. If you dump this out, so we're losing this. So this is, now when we add, my reaction example that I use for my seesaw teeter-totter, when something is added to a side, I put it on top. Pretend like you're dumping it in. That's what I did here, like you're adding more to it. But when we take something away, I put the arrow underneath. So we're pulling it out. That's what in my brain always worked. I hope it works for you. And I'm pulling this out. So this side's going to get lighter because I'm pulling you out. So what happens? Okay, we made some of you a nice thing. Oh, you're going to start pulling this out? Then what happened? It's like your friend Billy or Bonnie, or both, you can choose. You're seesawing with that person and they need to go to the bathroom. And so, well, if we don't want to lose all of Billy or Bonnie, their arm has to go to the bathroom, okay? Their arm says, I need to go to the bathroom. So they takes off. I know it's weird, but just roll with it, okay? So the arm runs away and goes to the bathroom. Well, what just happened to Billy/Barney? They got lighter, right? So that means we lost some of Billy/Barney, and this side goes, right, this side's going to be heavier because you lost some of Billy/Barney. So what do we have to do? We're going to have to make more of Billy/Barney in order to make up for the loss of the arm of Billy/Barney. I hope my analogy is working. I just came up with it, I don't know. And so we got to make more of this because you're losing product. Look, you're losing product. So in this case, we got to make more product on this side. So we're going to have to get this to shift back and replace the lost product. So we got to make more product. So these guys are going to have to, hey, get your act together, people. We need to make more of this. Okay, we're on it. Make more. So that means we're losing you and gaining more of you back. Yes. Make more product, shift to the right. Okay, that would be a shift to the right. The pressure on the gas is increased. This is kind of interesting. If we look, we got a gas. This is 1 mole of gas, because our coefficients are moles, and 1 mole of gas here. So there are 2 moles of gas on this side, and 1 mole of gas on this side. And we're balanced. But now you increase the pressure. Now we know from gas laws that pressure has a huge influence on gases. So by increasing the pressure, who's going to be more effective? Why? There are 2 moles of it, twice the effect on this side than this side. So this side gets affected more. So it's like dumping more of this stuff in. So if I'm use that arrows that I've been using before, it's kind of like, I'm not adding more gas, but I'm affecting them more. So by adding pressure, now we're adding pressure on both sides, but I'll go ahead and put the arrow here. We're adding pressure on both sides, but now you can see that there are 2 arrows here and 1 arrow here. This side's going to be more affected. Okay, when we add, more of this now going to be more effective. How am I going to relieve that added stress to the left? We need to make more of this. So we need to decrease the amount of these and increase the amount of these, so this side can be just as affected as this side. We're going to shift to the left. We'll have to shift to the left to cause this side to have more and these side to have less moles, so we have an equal number of affected molecules. Okay, that would be a shift to the left. Okay, all right, one last one here. A catalyst is added to the reaction mixture. If we remember what a catalyst is all about, Charlie Brown, a catalyst doesn't get involved in the reaction. It allows the reaction to happen faster, lowers the activation energy. So it's easier for the reaction to do its thing. So if you had a catalyst in, this will go to equilibrium faster. That's all it means. It's not going to affect either side. So the catalyst just goes right here. It doesn't get put on either side of the seesaw. So that would be like, you and your buddies are all balanced out on the seesaw, and some kid comes up and they stand right on the seesaw on the pivot point. Doesn't do anything, right? You're still in equilibrium. If the kid's standing right on the pivot point, doesn't tilt it either way. Doesn't affect it. So a catalyst will have no effect. No effect on shift to the left or shift to the right. Okay? It just speeds up the time it takes for the reaction to get to that equilibrium point, but it doesn't affect either side. So no effect with the catalyst. All right, okay, that's it. We wrap this up. That wraps up the stuff for today. Hope that all made sense to you. If not, go back, watch video again, or ask questions in Zoom chat. Okay?